doesn't tell us the shape. So we can think about this in terms of valence shell electron pair repulsion theory, that those atoms on the outside there and that lone pair of electrons are all going to push away from each other, and that'll give us a three-dimensional shape. To help us predict that, we'll use the AXN notation. So A, that's our central phosphorus atom. We have one of those. X is the number of atoms attached to that central phosphorus atom. So we have 3 chlorines. And then N, that's the number of lone pair electrons, unbonded electron pairs. And we have that 1 right there above the phosphorus. So we'll put a 1 right here. So now that we have an AX3N, we can look that up on a table and tell the molecular geometry for PCl3. So as we go down our table here on the left, we see we have AX2, AX3, down to AX2N, AX2N2. At the bottom we have AX3N, and that is trigonal pyramidal. It also gives bond angles of 109.5, and those are rather general. If we actually look at the molecule, we'll see that it looks like this, where the phosphorus is in the center, and we have floating above it that lone pair of electrons. And the angle that we're talking about is right here, and it actually turns out to be, when we look at experimental data, to be 100 degrees, not that 109.5. So the AXN notation gives us a good idea about the bond angles and a very good idea about the shape of the molecule. So PCl3 has the molecular geometry of trigonal pyramidal. Here we are at the Lewis structure. We can see that there are 3 oxygens and there's 1 lone pair of electrons. In accordance with valence shell electron pair repulsion theory, they're going to spread out. They're going to push away from each other, so they're as far away as possible. We'll still bonded to that central chlorine. When they do that, that's what's going to give us our shape. We can use the AXN notation to help us determine, to predict that shape. So A, that's the central atom. That's our chlorine. We have 1 of those. X, that's going to be the number of atoms bonded to that chlorine atom. We have 3 of those. And then N, that's the non-bonding electrons, or the lone pair of electrons there, and we only have 1 pair of those. So we have AX3N, and we can look that up, and we can see going down our table here at the bottom, there's AX3N, and it's a trigonal pyramidal or trigonal pyramidal molecular geometry, and the bond angles are 109.5. Since this is a general table, they're not going to be exactly 109.5, but they'll be around there. So we end up with a molecular geometry of trigonal pyramidal. Let's look at, we can see there are 3 atoms, 3 oxygen atoms, bonded to that central carbon. And according to valence shell electron pair repulsion theory, those 3 oxygen atoms are going to spread out as far away from each other as possible. That should give us a trigonal planar molecular geometry. We can also use the AXN notation to make sure we have the correct molecular geometry for CO3 2-. A, that's the carbon, and then X, that's the number of atoms bonded to the carbon. There are 3 oxygens, so we'll put a 3 there. And N, that's the number of non-bonding electron pairs. All of the electron pairs are involved in chemical bonds between the carbons and the oxygens, so we can just ignore N. So you could have memorized that AX3 is a trigonal planar molecular geometry. Or if you had a table available, you could look it up. As we go down the table, we see AX2, and right below it, that's AX3, which is trigonal planar with bond angles of 120 degrees. We could also look at the 3-dimensional structure to confirm that and see what a trigonal planar molecule looks like. So we have a carbon in the center, and then we have the oxygens out here. And you can see they're spread out as far away from each other as they can be, and they are in a plane. We can also see that the bond angle right here, or right here is 120 degrees. So that's... To find the molecular geometry of NH3, we'll first look at the Lewis structure. We want to visualize those 3 hydrogens in that lone pair of electrons there spreading out as far away from each other as they can, and that will give NH3 its shape or molecular geometry. And that's going to look like this right here. In essence, those valence shell electron pairs around the hydrogens and then that lone pair of electrons above the nitrogen there are going to repel each other, and that's going to give NH3 its shape. In this case, the shape is trigonal pyramidal, sometimes called trigonal pyramidal. We can also use the AXN notation to determine the molecular geometry of NH3. A, that's the central nitrogen there. X, that's the number of atoms bonded to nitrogen, and we have 3 of those. And N, that's the number of lone pair electrons. We have 1 lone pair of electrons. So we can either memorize that AX3N is trigonal pyramidal, or, if we're allowed to, we can look it up on a table. So if we go down here, we can find AX3N right here, and that is trigonal pyramidal, and also the bond angles are 109.5 degrees. So, hi, this is Dr. B. Let's do the pH3 Lewis structure. On the periodic table, phosphorus group 5, 5 valence electrons, hydrogen group 1, but we have 3 of them for a total of 8 valence electrons. We'll take and put the phosphorus in the center. Hydrogens always go on the outside. We have 3 of them. We'll put 2 electrons between each of the atoms to form chemical bonds. We've used 6 valence electrons, put the last 2 in the center for a total of 8 valence electrons. So we've used all 8 valence electrons. Hydrogen has 2. This one hydrogen has 2, as does this. So all the hydrogens are okay, since they only need 2 valence electrons for a full outer shell. And then the phosphorus in the center has 8, so it has a full shell.